Hey everybody, welcome back. Mike here. I'm really excited for today's video because we're returning from our tangent into graphics and getting back into sound. We're going to review digital sampling, take a look at the fast Fourier Transform and analytic signals and how they're useful to us, and then briefly recap filters, which we covered in episode 2. Then we will take a sneak peek at the modifications that I've made to the synthesizer from episode 2, which we'll dive into in the next video. So all these concepts will be used in the next video to explain how the synthesizer works, and all of this is in preparation for later videos. So enjoy this one, let's go! So here's what we're going to cover in this video. Feel free to pause, rewind, and rewatch as needed. The first thing to remember for this video is that sound travels in waves, that is, some quantity going up and down in a repeating pattern. Specifically, sound in air is made by air pressure going up and down over time. We can measure the air pressure using a microphone, which converts changes in air pressure into changes in voltage carried by a wire. The voltage change is analogous to the original pressure change, so we call this analog sound, from the same root as analogy. We can measure the voltage tens of thousands of times per second, giving us a list of numbers representing the voltage at each measured point in time. This is called digitizing. Digitization is the process of turning something into a list of numbers representing separate measurements. The number of measurements made per second is called the sample rate. We can record sounds with frequencies up to 1/2 of our sample rate, which is called the Nyquist frequency. So, if we record 48,000 samples per second, our sound can contain frequencies up to 24,000 Hz. You may recall that the limit of human hearing is about 20 kHz, so 48 kHz sampling is plenty for most of our needs. Digital sound can then be converted back to analog by generating the voltages described by the list of recorded numbers. Those voltages are then amplified and sent to speakers, which convert electricity into movement, which in turn creates changes in air pressure, and those changes in air pressure reproduce the original sound. Digital sound is incredibly useful to us because we can use math to transform the sound virtually limitlessly. For a simple example, we can multiply every sample by a constant value to change volume, either louder or quieter. Most streaming services transmit two separate streams of numbers for sound, left and right. If a sound is played at the same volume in both left and right channels, it seems to come from the middle. Varying the relative volume of the two channels makes the sound seem to move back and forth between the left and right speakers. Sending two separate channels to be played by two speakers is called stereo sound. Sending just one channel is called mono sound. The next thing to review is the circular nature of waves. We saw in episode 1 that sine waves are really just one dimension of circular motion in two dimensions. A circular sine wave can be shifted earlier or later in time, or clockwise or counterclockwise in rotation. This is called phase and is measured as an angle of rotation. We saw in the second episode that more complicated waves can be created by adding a whole bunch of sine waves. Put these ideas together, and we can represent any complicated sound using combined circular motion. There are lots of great videos from others about digital sound, so I've created a playlist with some of those videos, a link to which is in the description. Feel free to mention more good videos and channels about sound in the comments. The mathematical tool we use for turning sound into an equivalent combination of simple sine waves is the fast Fourier Transform, or FFT. The FFT takes a list of amplitudes recorded at regularly spaced points in time and returns a list of amplitudes at regularly spaced frequencies. We can split a sound into overlapping slices of, say, 800 samples, then calculate an FFT for each slice to see how the sound evolves over time. These slices are called windows. So once again, for sound waves, the FFT gives us a discrete, finite list of sine waves that make up the sound. There are positive frequencies on the right and negative frequencies on the left. In the middle is the zero frequency, sometimes called the DC or direct current component. Let's slow this down and take a closer look. All frequencies in an FFT are integer multiples of some base frequency. Each frequency is represented by a 2D vector with an x and a y, or equivalently a complex number with a real and an imaginary part. The length of this vector gives the amplitude of the corresponding wave, and the rotation gives the phase. These numbers are coefficients in the equation for a sine wave. Frequencies that don't fall on one of these exact frequency samples get split between the closest neighboring samples with changes in phase. These frequency samples are sometimes called bins because all frequencies get sorted into these separate frequency bins as if they were containers for a range of frequencies. For sound waves, the positive and negative frequencies are a mirror image of each other. But wait a minute, how can frequency be zero or negative? How can you do something negative 60 times per second? Remember that each wave is actually not just a flat sine wave, but motion around a circle. Positive frequencies represent counterclockwise rotation, and negative frequencies represent clockwise rotation. The zero frequency represents no rotation and is just a constant shift. The complex number form of each frequency serves as the coefficient in the circularized wave equation. When all these circular waves are added back together, the clockwise and counterclockwise rotations cancel out to give us the original flat, one-dimensional wave. If we ignore the clockwise negative frequencies and add up the positive frequencies, we get our original sound wave's equivalent circular-ish motion. Notice that the previously flat waveform turns into a spiral as we remove the negative frequencies. Every sound can be represented in this circular spiral form by removing its negative frequencies. Any wave in this form with no negative frequencies is called an analytic signal. We'll explore the analytic signal form of sound and why it's useful in the next video. So why have negative frequencies at all? Because the FFT is used for 2D motion as well, not just 1D sound. You can find more videos about the Fourier Transform in the playlist linked below, and feel free to ask questions and discuss in the comments. Finally, in episode 2, we also looked at filters, which are functions that can change the amplitude and phase of the different component frequencies that make up a sound. Removing the high frequencies makes a sound seem muffled, and removing the low frequencies makes a sound seem thin and metallic. The bass and treble knobs on an old stereo are examples of filters. We'll make more use of filters in this and future videos. So those are our basic concepts for this video. Alright, having reviewed those concepts, let's take a look at the synthesizer that we're going to dive into further in the next video. We'll use the synthesizer to explore concepts like envelopes, wave shapers, and filters. I've assigned camera changes to keyboard buttons so I can take you on a tour through the synthesizer features in the next video. For now, let's dive into a demo song. So I hope you enjoyed that demo and the review of digital sampling, the discrete Fourier transform, and filters. We'll dive into that synthesizer in the next video. So subscribe so you don't miss future videos, and let me know in the comments if you have any suggestions or questions. Thanks for watching and have a good one. If it's not good enough, too bad. That's what you get. This is the video. It's done.